Hi, I'm Ranveer. I've been at Microsoft 16 years. I did my PhD in computer science at Cornell. I'm from Jamshedpur in India. I went to India, did my undergrad there, and right after that, I came here to the US, did my PhD, joined Microsoft Research. I've been doing a lot of work at Microsoft Research on networking. My background is in networking technologies. But then I've been, every 5 years, I kind of start a longer term project, which it could be in the kind of in the blind spot of what Microsoft is doing. We are encouraged to do those things which are longer term, risky, might or might not take off. And towards that, in 2005, I started a project called TV White Spaces, which I'll talk a little bit about today. 2010 is when I started research on batteries, like what's the future of energy. 2015 is when I started this project on FarmBeats. And I know it's 2021. In 2020, there are two things that I've started. One is on sustainability, and I'll talk a little bit about that, what we're doing there, and also on space communications, satellites, and the future of that.
Wow, it gets more exciting every time. All right, please go ahead.
Yeah, so today I'll talk about data-driven agriculture. And the hope is that, well, you'll get motivated to see what can technology do when you think of solving some of the world's hardest problems. Anand talked about some of them, and here I'll talk about the world food problem. So, hello again, everyone. So I'm Ranveer Chandra, and today, this is a project that I said I started in 2015. Just before I start, I don't have an agriculture background. As I said, I'm not an agriculture scientist. I'm a computer scientist. But growing up, I spent a lot of time growing up in Bihar. This is my grandparents used to live there. For people from India might relate to this, that a lot of time growing up you spend with your grandparents. So every summer and winter vacation, I would go to their farm in North Bihar. Getting there was quite a challenge. And as people, some of you might know, Bihar is among the poorest states in India. Back then, like 3, 4 months a year, I would go. The first 18 years of my life I spent in those farms. Back then, I did not like anything to do with agriculture. These farms, they did not have electricity, they did not have toilets. It wasn't the most pleasant summer and winter vacation that you would expect. I did eat a lot of mangoes, but it wasn't quite pleasant. I wasn't looking forward to these vacations. But that said, I did get exposed to a lot of poverty in that part of growing up. I did see a lot of primitive forms of agriculture, like bullock-driven tractors, like hand-based seeding, and so on. So that was one of the reasons that I started this project, something that could help the people in that part of the world, in the emerging markets, the smallholder farmers, do better. But in fact, the goal is much bigger. That is, as many of you might know, the world has a food problem. We need to grow more food to feed the growing population of the world. And it is not just, so compared to today's levels, it's about 50% more food needs to be grown by 2050. It's not just about growing more food. You need to give good, nutritious food to the people. And you need to grow this more nutritious food without harming the planet. The amount of arable land is not increasing. The water levels are going down. The soils are not getting any richer. So then the question is, given all of these challenges, how can you sustainably grow more food, more good food? One of the most promising approaches to address this problem is that of data-driven agriculture. One of the things you could do, for example, with data-driven agriculture is you could map every farm in the world with data. For example, what is the soil moisture level 6 inches below the soil? What's the soil nutrient level? How much fertilizer should you put everywhere? What's the soil temperature level? If you could build maps like this, it would enable technologies such as precision agriculture. That is, if you had a map like this, you could put water only where it is needed. You could put fertilizer only where it is needed. And this technique of precision agriculture has been shown to improve yields. It has been shown to reduce costs. It's also better for the environment. That is, it's reducing costs because you're putting water only where it is needed. You're putting fertilizer only where it is needed. It's also better for the environment for the same reasons. You're not wasting water. You're not putting more chemicals than are needed in the farm. And it is not just about the farm, not just about production agriculture. The entire food supply chain, all the way from input companies to equipment companies to the farmer from producing the food to the food supply chain, food distribution, food warehouses, the logistics supply chain companies, the food processors. Every entity in the food supply chain would benefit from data and data-driven insights. In fact, if you could start sharing this data across the food supply chain, it could then unlock even more efficiency, even new business models. For example, you could do things like traceability. You could figure out what, like for example, for food safety, once there is an outbreak, you can know where that outbreak came from if this kind of data sharing was in place. Similarly, you could do precision agriculture. These digital advisors could then know what type of seed is planted, what type of chemicals you're using, and then give you advisories on what to do where in the farm. There is a new emphasis on sustainable agriculture. That is, you could then farmers could be reimbursed for using the right agricultural practices, things like planting cover crops, using no-till or reduced-till. For that, the farmers need to share their data of what they did in the farm with other entities in the food supply chain and even in the carbon market. The thing is, even though these benefits of data-driven agriculture and digital agriculture are well known, these technologies haven't really taken off. And just to put this in perspective, the precision agriculture was proposed back in the 80s. It's been over 30 years since the time it was proposed, and the technology hasn't really taken off at scale. And the biggest reason is that these technologies are still very expensive. Just to put it in perspective, I was in UC Davis. This was a few years back, 2017, when there was an expo going on and there were many companies presenting their latest and greatest precision ag equipment. And the cheapest, for example, sensors that we use in precision agriculture were 5 sensors for $8,000 and a recurring cost. At which point, for most farmers, this is just way too expensive. What is the return of investment of putting a few sensors in the farm? So this is the reason we started this project, and we started addressing some of the most fundamental reasons why these data-driven technologies are more expensive, and I'll talk about a few of them. So one of the biggest reasons existing solutions are expensive is because of connectivity on the farms. The farmer's house has some sort of internet connectivity to the cloud. Many farmers, they pay for broadband, but they have like 1 to 3 megabits per second connection. But the actual farm could be a few miles away. Even though connectivity might exist when the farmer plants the seeds, a lot of times where the plants grow, the connectivity is gone. So then the question is, how will you transmit data from a farm which is a few miles away? Data from sensors, from drones, from tractors, from cameras, all of this stuff to the farmer's house. To address this problem, we use a technology that I personally have been working on since 2005 called TV white spaces. What the TV white spaces enables is, imagine if you have a Wi-Fi router that you could access miles away. That would be cool, right? Right now, as soon as you exit your house, your Wi-Fi disappears. The particular technology we built was a way to take this Wi-Fi signal and put them in empty TV channels. This is TV you watch using antennas. You know, when you browse through TV, on certain channels you get a transmission, the other channels are just white noise. With this technology, we were able to send Wi-Fi signals on these noisy TV channels in a way that doesn't interfere with your TV reception in the adjacent channel. The interesting thing about TV channels is that TV towers are where people are. You have TV towers in Seattle, in DC. The farms are away from the cities. If you turn on a TV in the middle of a farm, most of the channels are just white noise. The more noisy channels there are, the more available capacity there is. So we're talking of, even if there are 20 TV white space channels, we're talking of over half a gigabit per second of available capacity in the middle of a farm. So, and the other interesting thing about TV white spaces is that the TV spectrum has excellent propagation characteristics. It can go in UHF TV channels, your signals can go 4 times farther. In VHF, they can go 12 times farther. In free space, through trees, crops, canopies, these signals just keep going through. So our vision here is, just like Wi-Fi connects your house, this spectrum can be used to connect your entire farm. It's not just at Microsoft though. Right now, while we are TV white spaces is one of the innovations, we are also looking at other ways. For example, private 5G. Microsoft had started an Azure for Operators group. We are looking at whether we can do a private 5G deployment, whether we can use space connectivity in the middle of a farm. The key goal here is to use a combination of technologies to then enable low-cost connectivity in the middle of a farm. The second challenge is about AI. The first challenge is about data. That is, how do you get data from the middle of a farm? Because when you're talking of AI, your AI is typically as good as your data. So you need that good bandwidth to drive your AI algorithms. The second challenge is, I talked about building these kind of maps of farms. For example, what is the soil moisture level 6 inches below the soil throughout the farm? If you have to build an accurate map like this, you would need lots and lots of sensors, say a sensor every 10 meters. But putting a sensor every 10 meters is expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So the key question we asked was what you're seeing on the last point here. That is, can we build an accurate map like what you're seeing here for soil moisture, soil temperature, soil pH, and others using a very sparse sensor deployment? The way we address this problem is using aerial imagery and using AI. That is, what we do is first we get an aerial image of a farm. That is either using drones. These drones have a camera at the bottom. They can cover large areas very quickly. We use that to fly an area, cover an area, and then we use computer vision techniques such as generating a 3D point cloud and then stitching it together to build these kind of high definition maps of the farm. Well, drones are great, but drones can't be used everywhere. That is, in one country in Africa where we wanted to fly drones, we were asked to get permission from the Ministry of Defense, at which point it wasn't going to happen. So then instead of flying a drone, we came up with another low-cost technique. The question was, well, drones, there are regulatory challenges in some countries, in the emerging markets where there are small farms, like the farms I used to go to when I was small. Those farms, the drones are still expensive at over $1,000, and they have limited battery life. So then the question was, how are you going to get an aerial image of a farm, of a small farm, if you can't fly a drone? We came up with another method. We use helium-filled balloons. These are about 4 feet in diameter. This is very low tech. That is about 4 feet in diameter balloon, which is tethered to the ground. And then what we built was a weatherproof mount where you could put your phone with your camera facing down and a battery pack attached to it, which can then take images of the farm. And in fact, in places like India or sub-Saharan Africa, where labor isn't expensive, someone could just walk around with the balloon or put it on a bicycle and just drive around, and you have an aerial image of the entire farm. We then use computer vision and AI techniques to stabilize the imagery and build these kind of orthomosaics, the panoramic views that you're seeing of the farm. Well, drones and balloons are great, but of course, you can't get an image of every farm using drones or balloons. So for those, we use satellite imagery, where satellite imagery is not as high resolution, but at least it gives you some coverage for most farms. So then once you get this kind of a view, this panoramic overview of the farm, what we then do is we figure out using AI techniques, what are the best places to put the sensor? You don't need to put a sensor every place. You can figure out which places look similar, and then out of those, just put sensors in one or a few of those places. We do this intelligent sensor placement. And then what we do is wherever you have sensors and you have an aerial image, corresponding to that pixel of where the sensor is and the corresponding value, the RGB, the multispectral or the hyperspectral pixel value, we use that to train the model. And then we use that trained model to predict these values in other parts of the farm where you don't have sensors. So we use this machine learning approach we've used this to predict soil moisture, soil temperature, soil pH. We are doing it now for soil carbon and many other techniques. We wrote a paper on this, which was published in a top-tier computer science conference. And there we showed in that paper that using aerial imagery along with the sensors is 3 times more accurate than existing schemes that do not use aerial imagery. So we did this for, as I said, for soil temperature, soil moisture, and soil pH. One of the things I mentioned in the previous slide was we use satellite imagery for generating the farm images. Well, one of the biggest challenges with satellite imagery is that more than 77% of the Earth is covered by clouds. When it is cloudy, you really can't see what's happening below the clouds. For that, one of my interns, he was from MIT, he spent the summer here. He came up with this technique, and now Peter, there are other people in the team who are actually leading this effort. We are building a system called SpaceEye, which can see through the clouds in satellite imagery. The way we do that, the way we do that is using data from another satellite that has radar in it, and then we use a new AI technique called partial observation GANs to generate what's happening below the clouds in satellite imagery. Here, what you're seeing on the left is what you get right now with satellite images. On the right is what we are able to generate using AI and using computer vision techniques called SpaceEye. So as you can see, even though it is cloudy, on the right, you're able to see how the farm is changing. The farmer's applying, irrigating, he's tilling, all of that stuff you can see, even though it's cloudy. The way we do this is we use another satellite that has radar in it. As you know, radar signals, they go through the clouds, they reflect differently from different surfaces, if the soil is moist, if the soil is dry, if it is a tractor and whatnot. And we use that SAR imagery to then generate what's happening below the clouds in satellite imagery. And we are very impressed with the results we're getting. Over 95% accuracy in 3 of the 4 seasons for summer, spring, and fall. And of course, here you're seeing this for farms. We've done the same thing for the port of Seattle. You could see ships coming and going, even though it was cloudy. We've done the same thing for construction sites. You could see a construction site come up, even though it is cloudy. The third challenge, the first challenge I showed how with TV white spaces, for example, you could significantly bring down the cost of connectivity. The second thing I showed was how you could use much fewer sensors than what you would otherwise need to generate very accurate maps for farms. The third challenge is, well, you could get large amounts of data from the farm to the farmer's house, say using TV white spaces or private LTE, but the connection from the farm to the cloud is weak. Many farmers, they pay for broadband, but all they get is 1 to 3 megabits per second connection. And this connection is also intermittent. There's a farm in upstate New York where we had done a deployment. Every time there was a snowstorm, the farmer's internet connection was likely to go off. So then the question is, if you could transmit large amounts of data from the farm to the farmer's house, but can't really send it to the cloud, how will you bring benefits of all of this data to the farmer? To address this problem, our key insight was that most farmers, they have a PC. If they don't have a PC, we'd ship them a PC form factor device. That PC would sit in the farmer's house or office and do a lot of compute sitting in the farmer's house and office, do a lot of computer vision, a lot of AI sitting in the farmer's house or office. Just double clicking on what's running on the edge device. Everything you're seeing in this big gray box is running on the edge device. It gets data from sensors, from drones. It does the panorama generation, combines with sensors to build heat maps, on top of which you could start generating these different agricultural services, for example, for precision irrigation, pH, and others. We also ingest data from cameras, where you could be running deep learning on the edge. I'll talk about one of those scenarios. And all of this data is then lazily synced with the cloud. We also have unique storage that runs on this, so that not all the data needs to be sent to the cloud. We also have a web server so that when the system, when the internet goes off, the system can keep running even when it is offline, and you can keep accessing it. So while this was in research, we did several deployments in different parts of the world. And I'll talk about a few of these farms, all the way from like a small farm to a 9,000 acre farm. This is one of the things we do is when you put a sensor, we were able to predict not only tell you what the sensor values are right now, but we would predict what these values would be up to 5 days in advance. So for example, here what you're seeing on the right is soil moisture and soil temperature. If you look at the red bars, even up to 5 days in advance, the error is less than 8%. The way we do this is and the reason this is important is, for a farmer, weather plays a very important role in everything a farmer does. They need to know when is it going to rain, what's the wind, what's the temperature. All of these are very, very important parameters for a farmer. The way we did this prediction was, and by the way, even though they're important right now, a farmer looks at the weather forecast, but the weather forecast tells you the weather at the weather station, not what's happening in the farm. The way we made these hyperlocal predictions was we took data from 50 weather stations across Washington state, and we used that this was over the last 7 years at 15-minute intervals. We used that to train a model. And then we used that trained model to start making very hyperlocal predictions of what's happening in the farm. At the bottom left, you see a testimonial by the farmer. The farmer was there was a part of the farm that was heavily infested with weeds. He was looking to spray chemicals in the farm. He looked at the predicted weather forecast. It said it was going to be 42 degrees. We said it was going to be 31. It was actually 30 degrees. It was below freezing. It was good he didn't go spray chemicals in the farm because otherwise he would have lost his crop. The other way he uses this AI method of making micro hyperlocal predictions is every time he takes out his tractor, this farmer farms 9,000 acres spread across 45 miles. Every time he takes out his tractor, he would look at the predicted wind forecast to see how the wind is in different parts of the farms, different fields, so that he goes to the fields where there is not enough, the wind is not strong, because otherwise the spray is going to be not as effective. This is another use case I like talking about. This is a farm in upstate New York. The farmer wanted to know how his cows are doing once they're out in pasture. So for this case, we flew the drone, we transmitted the data over the white spaces to an edge device, and within 30 minutes, we could start flagging things like from left to right, the grass is growing back well, there is a water puddle that needs to be fixed before the next planting season, the cows are pooping well, which is also important information for the farmer. This is deep learning on cow poop. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is a farm here in Washington State. We used to do a lot of demos here. This is a smallholder farmer who sold his produce in the farmers market and to restaurants. We showed the farmer these beautiful pictures. We used to do a lot of demos in this farm. Bill Gates spent several hours. He wrote about this in Gates Notes as well. So we show the farmer these beautiful pictures and overlay it with data. For example, on the bottom left part of the farm, we were able to flag that that part of the farm is still moist, even though we did not have a sensor over there. This is after the farmer had applied lime. We were able to flag that these dark parts of the farm are still acidic. The farmer needs to reapply lime before planting the seeds. This is another use case in upstate New York, where we had a barn with multiple cameras streaming data over the white spaces to an edge device. We're using AI. We are able to see how the cows are moving, whether a cow is sick, and then flag that information to the farmer. You can think of that like deep learning. This is like a baby monitor for cows. You can see where a cow is sick and immediately take action. So this was all in research when up to 2018, I was in the Microsoft research side, and I moved over to the product side and we helped ship my Azure FarmBeats as a product. So the way we shipped it as a product is as a cloud solution, a cloud platform where, right now there are several ag tech companies. They would ingest different types of data from sensors, from drones and so on. Not all of these, but some of them. They would write their own data ingestion pipelines and then build their solutions on top, their AI solutions on top. What we did was we took the common portions and said, based on all the things we are doing, we can build a really powerful cloud platform for other ag tech companies that are building data-driven agriculture solutions. So with that, in the cloud, we've written this data ingestion APIs. We work with partners, sensor partners, drone partners. These are companies that will then send their data to the cloud, where we have the data ingestion APIs. We do the transformation. We do for geospatial AI on top. And then this is a solution where FarmBeats is not a farmer-facing product. The way it gets to the growers is through partners, is through ISVs, is through other ag tech companies who would build solutions and take it to the growers. Just in a nutshell, what this provides, with what FarmBeats provides, is you can then specify a polygon, which could be a farm, a field, a set of fields, and then you can connect. For that polygon, we bring in all data for that particular piece of land, from sensors, from drones, from satellites, from weather stations, from tractors, all of that to the cloud, so that you can then start running your AI on top of that. And we've announced multiple partnerships. Last year, for example, we announced a partnership with Land O'Lakes, where Land O'Lakes has announced that they'll be building all their ag tech solutions on top of Azure FarmBeats. Similarly, USDA is building their sustainability platform. So a lot of the sustainability research at ARS is being done on top of Azure FarmBeats as well. In addition to just the research and the products, we've been taking other approaches to take the work that we do all the way. And I'll just talk about one today, one of these because of lack of time. It's on sustainability. As many of you might know, last year in January, we made a big sustainability commitment. Microsoft said that we're going to be carbon negative by 2030. That is, we are going to be putting in more carbon back in soil than the amount of carbon that we generate. And by 2050, we are going to remove all the historical carbon emissions that Microsoft has ever generated since the time Microsoft was founded. So then, first question, how do we get to carbon negative by 2030? So towards that, part of how we'll get there is by reducing our own emissions. We are going to make our data centers more efficient. We are going to make a supply chain more efficient. But that's not going to be enough. We need new ways to put more carbon back into soil. In fact, last year we announced, and we announced this RFP where we are looking at ways in which we can put this carbon back in soil. And interestingly, the reason I'm bringing it up here is agriculture is one way in which you could put this carbon back in soil. As you know, with plants, because of photosynthesis, they would take carbon from the air, carbon dioxide, and they would store it in the plant. They would emit oxygen, and the roots of the plants, they would put more carbon back in soil. But the key challenge with using agriculture as a way to put carbon back in soil is, one of the key problems is, how do you even accurately estimate at a low cost how much carbon is stored in soil? For which, again, right now we are building tools, including AI, to estimate what the farmer is doing in the farm to come up with some idea of how much carbon is sequestered in soil. The other work we recently did was for student kits. We actually worked with the Future Farmers of America, the FFA, to build these student kits, which we gave out to high schools in rural America. These are high schools where one of the biggest reasons, so what we did was we built this kit, we built a curriculum around it, and our goal with this kit is to bridge the skill gap, train people and train these students in rural America so that they are skilled with data, AI, and cloud tools so that they can apply for jobs which require more skills. In addition to that, with this training, they would be able to apply the techniques with AI, with IoT and others in farming, in their own farms. And in fact, one of the other hidden goals in all of this is to make this, to show that agriculture is cool again. One of the biggest problems in agriculture is the aging population of the farmers. Most of the next generation of farmers, they don't want to stay in farming. They want to go somewhere to the city. They want to do something else. Here, through these kits, we want to show that, hey, farming is one of the most advanced industries. You could be using drones, AI, space communication, all of that stuff, AI for this industry, and make agriculture cool again. So I want to conclude with just showing one. Let me see how to do this. I'll show one video of a farmer. This is in Eastern Washington, on how he is using FarmBeats in his farm.
Eastern Washington's my home. I describe it as one of the most beautiful places on earth. My father farmed this land before me, and before him it was his dad, and his dad before that. I'm a fifth generation farmer, and so I do have a very close connection to the land here. Farmers need a lot of tools to make better decisions. Any decision on a farm is really a big deal. Azure FarmBeats combines information from IoT devices, insights from machine learning, and serves it up in a way where other platforms are able to build off of it and help make a farmer more productive. The sensors measure temperature, wind, rain, humidity, soil moisture and soil temperature, CO2 levels, the solar intensity as well. One of the ways that the model can help make better decisions is temperature predictions. So that model will then tell you, oh, it's going to freeze tomorrow morning, and it's going to freeze, in the lower area. The whole field is not the same. So this year, when I have multiple sensors in one field, what I noticed was the soil profile on the top of the hill was different than on the bottom of the hill. And usually what we do is we plant the whole field the same. but it was so different that I seeded fewer plants up higher in the field and seeded more down lower. And then I could track it throughout the year with drone flights and with yield data at the end of the year. The big surprise is I didn't think it looked as good, but when I harvested it, the data allowed me to get a much higher yield than I was expecting. It's a very counterintuitive idea that you have fewer plants and yet they produce not just more, but they were producing twice as much. It's just the first year, but if I can do this every year, that's something that's really going to help our farm a lot. The way my dad used to farm and figure out what was going on in every field was you would walk through the field. So being able to know, what the soil moisture is like at a field that's 20 miles away is very beneficial to me. Family time for me is very important. I have 2 little kids, 2 little boys. Being able to save that time allowed me to spend more time with my family. I love being a farmer. I wish that it were easier sometimes, but that's why I harness every tool available to make it easier and make it something where I can continue farming.
Yeah, so with that, I just wanted to conclude and say, well, this is what we've been doing at Microsoft, and we've just scratched the surface. There's a lot more to be done. And we just recently wrote a paper. This is a paper that I wrote with the Gates Foundation on what are some of the challenges and opportunities for taking some of these techniques to the smallholder farmers worldwide. And there are a lot of new challenges that need to be addressed. And many of you on the call are students and still looking to build a career in AI. So I would encourage you, while you're doing it, think of some of these fundamental problems facing the world and how you can use your skill set to help address them. Thank you.
Many thanks, Ranveer, for this amazing talk. Tons of questions in the live chat for you to answer, but I'm going to just take a few, okay, for you. So one is, first of all, are these sensors available in Mexico?
Yeah, so we are continuing to add partners, and so this is built by partners, right? So like, for example, in the US, we have Davis Instruments. I think Davis Instruments is also available in Mexico, and we have Pestle Instruments. They are available worldwide. So yeah.
Awesome. And I know we have lots of folks watching you live from Jharkhand as well, actually. So one question is, almost every farmer has cell phone. Can we use cell phone cameras to send images of the farm?
Yeah, no, so that would be awesome if they could, right? So we are looking at ways in which we could get large amounts of data from the farm, right? The fundamental thing about data-driven farming is, can you map every part of the farm above the soil and below the soil and say what's not just what it is right now, what it was in the past, and using AI predict what it will be in the future? That's the fundamental problem. And there is no single answer to it, right? We have to use all available data sources, and farmers' phones. Yes, we need that as well. The hard part here is that all of these modalities are going to come in different ways. There's no standard way in which all of this data comes. So how do you clean this data? How do you extract metadata from it so you're getting the right piece of information? Because the last thing you want is AI interprets things in a completely wrong way and just predict something which shouldn't happen. The farmer believes it and actually ends up having losses. So those are the kind of scenarios we want to not enable. But that said, yeah, we need all possible data sources to really get to this vision of data-driven agriculture.
I see. And then also, can this solve global warming problems?
Yeah, so I think farming is one of the ways in which we could reduce the impact of climate change, right? Because, with global warming, one of the biggest reasons we have that is because of the greenhouse gas emissions. And the carbon problem, in a very simple way to explain it, is, well, carbon above the soil is bad, in the soil is good. So how do you get more carbon from the air and put it back in soil? One of the ways you can do it is through plants. Forests, of course, but plants do that, and agriculture does that. The trouble is, with agriculture, you need the right agricultural practices to keep this carbon in soil. farmers, what they end up doing is if you till the farm extensively, if you don't plant cover crops, if you just intensively do farming, you are then emitting more greenhouse gases. If you put lots of fertilizer, you're emitting more nitrous oxide. If you're tilling a lot, you might be generating more carbon. So agriculture can help solve the problem, but the farmers need to be educated to use the right agricultural practices so that the soils get richer. If the soils get richer, it makes the environment better as well. It can help mitigate the impact of climate change.
Awesome. So last question, last live question that you can always answer more questions on chat window. They run watershed projects, and how can this help?
Yeah, no. So watershed projects is a very interesting one as well. And there is a play between agriculture and the impact on water, because just the amount of, for example, if a farmer puts in more nitrogen, more fertilizer than is needed, what would happen is the excess fertilizer with water could actually go down and contaminate the water. So that's why, even if you have lawns here in Seattle, you should be careful about how much fertilizer you put. For farmers, that's important too. And this is one of the big problems in India as well. That is, we hear about the water problems in India. One of the problems is that of contamination. And so that's something where I think you need to, this is just one water problem where with agriculture and fertilizer, you could play a role. But with watershed projects, there are other things as well, in particular with what is the entire nitrogen cycle, the water use cycle from farms nearby, and the role they can play, how they can store more water with the right plants. There are things around agroforestry, and there's some very interesting research happening in this space. Most recently, we've been talking to ANL, the Argonne National Labs. They are doing some interesting work in this space too. But yeah, definitely there's this interplay between all of these sustainability metrics, including water, climate change, ecosystem, biodiversity, and agriculture has a big role to play in that.
Fantastic. Many thanks for all your live answers and also amazing talk. And of course, there's a few more questions for you in the chat. So with that, I want to thank you, Ranveer, for all your time. And just to let you know, as a next step, any other thoughts you want to have before you leave?
No, this is a great event that you're organizing here, and I know Soumya has a demo that she's put together. That's awesome. And yeah, for people on the call, do feel free to add me on LinkedIn and get connected. Would love to work with anyone who's passionate about this problem, and would love to see how we can keep pushing forward to help address this food problem in the world.
Absolutely. Thank you so much.